Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I am Sahib Noor and welcome to a new lecture of Electromagnetic Field Theory. In this lecture, we will study topics from chapter number 3. The title name of the chapter is Static Electric Field, and this is lecture number 12 of our course. The main topic of this lecture is to study the electric field due to many charges. As in previous lecture, we have derived an expression for the electric field intensity due to a point charge. So now we will have many charges in a space and we will find an expression for the electric field intensity due to these many charges. And then we'll restrict ourselves to two charges which are opposite in nature, and this combination in which two different behavior of charges are separated by a small distance is known as an electric dipole. So we will study the electric field intensity due to an electric dipole at a certain point in a region of space. Our last topic is to discuss the electric field intensity due to a continuous charge of a distribution, in which charge will be distributed in 3, 2 or a single dimension of a space, and we will find the electric field intensity due to these distributions. So let's start our topic which are related with the discrete charge distribution, in this slide we will first discuss the electric field intensity due to many charges at a single point, and then we'll start the electric field intensity for an electric dipole. So consider we have n point charges which are spread in three-dimensional spaces, and these charges are labeled as Q1, Q2, Q3, and we have n charges, and we have to calculate the electric field intensity due to these point charges at a point which are distance away from the origin, and the electric field intensity due to these point charges at a distance r is simply the algebraic sum of all the electric field intensities due to Q1, Q2, Q3 up to Qn respectively, and the expression of the net electric field intensity at the distance r is given by E is equal to 1 divided by 4 pi epsilon naught, and we have solution because we have n point charges and which is at a different position from the origin. But remember that we have to find the electric field intensity at a distance r. So here r represents the position where the field is to be calculated, and this is with respect to the origin. And if we put here k is 1, so it represents the electric field intensity due to point charge q1, and the point charge q1 is at a distance r1 prime away from the origin, and we will write the expression for other as well, and then we will sum up, and this is follow the superposition principle in which you can add the electric field intensity of individual charges algebraically, and we'll write the net electric field intensity as this. So the value of k, which is index, and it will vary from 1 to n. Now if we restrict ourselves to two charges of different behavior in nature, one is positive and one is negative, so it will make a pair of opposite charges, and if we separated these charges by a small amount of distance which is taken as d, then such a combination is called an electric dipole. So the magnitude of two charges will same, but the nature of these charges will opposite. And to find the electric field intensity at a distance r, we consider that the center of the dipole lies at the origin. So our origin for calculating the electric field intensity due to dipole is the center of the dipole. So in order to obtain the electric field intensity due to a dipole, we need a test charge, and we will have to place it at a point where the electric field is to be calculated. So the electric field intensity at that point is the sum of the contribution due to plus Q L minus Q, and can be written as E, which represents the total electric field intensity, is equal to E plus E minus. This represents the electric field intensity due to positive charge, and this represents the electric field intensity due to negative charge. And let our dipole lies along the z-axis, which are separated by distance d, which is very small as compared to r. R is the distance from the center of the origin to point P where electric field is to be calculated. And let mention some other distance. Let plus Q is R minus D by 2 distance away from point P, and minus Q is R plus D by 2 distance away from point P, and D by 2 is the half of the distance of the separation of the dipole. So our total electric field intensity will be like Q divided by 4 pi epsilon naught. Q is taken out from the bracket because the magnitude of positive and negative charge is same, and we have to write R minus D by 2 vector divided by its magnitude power Q, and minus R plus D by 2 vector divided by R plus D by 2 absolute cube. As in the denominator the power of the term is plus 3, and if we take it in the numerator term, so the power will be minus 3, and the parallel line represent that we have to take the magnitude of this vector, and to take the magnitude we have to write the term which lies in the parallel lines. We have to take square and square root. So for square root we write it as 1 by 2, which will multiply with the minus 3, so the whole power will be minus 3 divided by 2. And whenever there is square on a vector term, so we can split it and will write it in term of a dot product, and we will multiply these expressions and will obtain 4 terms in which 2 of them will result R dot D, and the remaining 2 are R square and D square divided by 4. As the distance between 2 point charges is D, which is very small as compared to R, so the square of the small parameter will give us a very small value, and we neglect them. And now we take R square as a common along with power, so the net power of R which is taken out will be equals to R minus 3, and we will have 1 minus R dot D divided by R square. The whole power is minus 3 divided by 2. So this term is very small as compared to 1, and we will now apply the binomial expansion and will apply on this term. So our binomial expansion will be equal to 1 plus nx. This is our n and this is our x. So we will write only the first 2 terms, because in binomial expression we have to take power of the x term, and as we know that the R dot D is very small, and when it is divided on a very large number, so its contribution to the whole expression will be neglected, and our result will be equal to approximately R power minus 3 into 1 plus 3 by 2 R dot D divided by R square. So we will write this for r minus d by 2 absolute power minus 3. And similarly, for the second term, we have r plus d by 2 absolute minus 3. And if we do the same process and extend it by binomial extension, our answer will be equal to r power minus 3 into 1 minus 3 by 2 r dot t divided by r square. And now we will insert the value of r plus d by 2 power minus 3 along with r minus d by 2 minus 3 in our main expression, and after some calculation our result for the electric field intensity due to a dipole will equal to q divided by 4 pi epsilon naught into r cube divided by r cube into 3 r dot d divided by r square into r minus d. And here if we multiply q inside the bracket, and we will have a new term to define, and this is known as the electric dipole, which is represented by P if Q is multiplied with the separation of the dipole. And so P is the product of magnitude of charge along with the distance of the two oppositely charged in the dipole. And P is a vector quantity, and the direction of the electric dipole moment is from negative to positive charge, which is opposite in the direction of electric field, as electric field is from positive to negative. Now, in terms of P, the electric field intensity can be written as 1 divided by 4 pi epsilon naught or cube into 3 r dot P into r divided by r square minus P. As our dipole lies along the z-axis, so P can be written in terms of magnitude along with direction. So the direction of P is in the positive z-axis. So P is the magnitude of dipole moment and Az is the direction. Now we can express a Z in terms of the spherical polar coordinates, which are AR cos theta minus A theta sin theta, and the dot product of R with P can be obtained by formula of dot product, which is RP cos theta. So write the value of r dot p and the direction of and p. So our electric field intensity in spherical polar coordinate will be p divided by 4 pi epsilon naught r cube into 2 cos theta into ar plus sin theta a theta. Now in this slide we will discuss the electric field intensity due to a continuous charge distribution. In previous slide we have discussed the electric field intensity due to a point charge or electric field intensity due to a discrete charge. For a point charge, the electric field intensity can be written as Q divided by 4 pi epsilon naught into r square, and AR is the radial direction of the electric field intensity at a point P. Now, if the charge lies in the continuous manner, so we will discuss the charge density instead of a charge. So we have three charge density: volume charge density, surface charge density, and linear charge density. This symbol is known as a rho, which represents the charge density. So in this figure we have a distribution over three-dimensional surface. So our charge element dq is simply as a product of charge density times the volume element, and this can be written as rho v is equal to charge element divided by volume element, or delta q divided by delta v, such that delta v approaches to 0. and the unit of volume charge density is coulomb per meter cube. And in differential form, it can be written, the charge can be written as dq is equal to rho v dv. And if the charge distributed on a two-dimensional surface, so the differential charge can be written as the product of surface charge density into area element. So here the sigma and dA represent a different notation, but we will represent surface charge density by rho s, and can be written as delta Q divided by delta S. The unit of surface charge density is coulomb per meter square, and the differential charge dq is equal to rho s ds. And if the charge lies on a straight line, which is known as the linear distribution of charge, so the charge element dq can be written as rho l dl. Here we write lambda dx, which represents the notation of a different book. But rho l is equal to delta q divided by delta l, and the unit is coulomb per meter, and the differential form of the charge in terms of linear charge density dq is equal to rho l dl. And the electric field intensity due to any length and any charge element can be written as dEr, which represents the radial direction of electric field intensity, and as our charge element is dq, so our main formula q divided by 4 pi epsilon naught divided by r square will equal to dq divided by 4 pi epsilon naught into r square in the radial direction. So in order to calculate the electric field intensity due to a continuous charge distribution, let the total charge q is distributed over a three-dimensional region of space, and then we take a volume charge element which occupy a volume element dv, and we have to calculate the electric field intensity due to this charge element at a distance r. So our expression will be equals to dEr is equal to dq divided by 4 pi epsilon naught r square into ar, and this implies that the charge can be written in terms of charge density times the volume element. So for dq we write rho v dv prime, and now we can also apply the definition of unit vector. A unit vector ar can be written as a vector divided by its magnitude. So our vector is r and its magnitude is r, so r vector divided by r, and the denominator r square will multiply with the r of the magnitude of the unit vector, and we will have r cube along with the r vector. And to find the net electric field intensity due to total charge, we will integrate the above equation. So here we integrate this term, and our total electric field is equal to ER. And at the right hand side, we also put the integration sign. So we have some constant terms in this expression which will be taken out from the integration, and our net electric field intensity due to volume charge distribution is equal to E1 divided by is equal to E, which is equal to 1 divided by 4 pi epsilon naught integral rho v r vector divided by r cube, which is the scalar part of r, and we will integrate it over the three-dimensional space. So this is the volume integral. And if the charge distribution lies on a plane or a two-dimensional surface, so the electric field intensity due to A surface charge distribution can be written as E is equal to 1 divided by 4 pi epsilon naught integral rho s r vector divided by r cube ds prime. So this represents a surface integral. And if the charge distribution is lie on a line, and we will write the electric field intensity due to linear charge distribution is E is equal to 1 divided by 4 pi epsilon naught integral of rho L r vector divided by r cube dl prime. Remember that these red r represent the vector form of the distance, vector form of the separation where the electric field is to be calculated from the charge element. So at the last part of this lecture, we are presenting an example in which we have to determine the electric field intensity of an infinite line of charge whose linear charge density is a constant. So we consider that the charge is distributed on an infinite line which is taken along the z-axis, and we consider the center of the line is our origin. So we have half positive half part of this line along the positive z-axis and half part of this line in the negative z-axis, and we have to calculate the electric field intensity at a point P which is distance small or away from the center of the line, and we take a charge element on the positive z-axis, and first we will calculate the electric field intensity due to this charge element. So it will be a differential electric field intensity, and which is r distance away from a point. So our net electric field, if we place a positive charge over here and we consider that the net charge is the overall charge is positive, so this charge element will repel this charge and the electric field intensity will be in this direction, and the line symmetry is resemblance with the cylindrical coordinate. So we take the cylindrical coordinate which are r, phi and z. So we will have two components of the DE. One is along the z-axis, one is along the radial axis. So if we take another length element, another charge element on the negative axis, which is at the same distance from the center of the origin, and we will have net electric field in this direction, and then we'll have two components as well, the radial component and the z-axis component. So we will let us see that the z component of this small electric field intensity will cancel because they are in opposite direction. So the electric field intensity due to a linear charge distribution can be written as 1 divided by 4 pi epsilon naught integral rho L r vector divided by r cube, which represents scalar part of r, and we will have a length element as well. So as the charge distribution lies along the z-axis, so our length element will be equal to dz, and the vector r, which is the resultant vector of z component and the radial component, and as our this is our resultant vector r, and this is come from the combination of z which is in the negative direction, so we will have a negative side with the z, and the radial vector is always positive, so r has a two components, the radial component and the z component. So the electric field intensity due to a charge element is represented by dE, and rho L dl prime in this case will equals to rho L dz, as the length element is taken as a dz. So by putting the value of r and r cube, r represents the magnitude, so we will have to take square and square root of the component of r. So by taking the square of r, we will have r square. By taking the square of minus z, so we will have plus z prime square. And as here we have 3, so our power will be 3 by 2, as 1 over 2 is the value of the square root. And we have two terms, the radial term and the z term, so we can split the electric field intensity as a radial electric field intensity and electric field intensity which is along the z-axis. So we can also write the magnitude of the radial component of electric field intensity and the magnitude of the electric field intensity along the z-axis. And as we have seen from the picture, we can decompose dE into its component in the AR and AZ direction, and it is also easy to see that for every rho LdZ at the positive Z axis, there is a charge element rho LdZ at the negative Z axis, which will produce the dE with the components dEr and minus dEz. Here we have plus dEz, and at the negative Z axis we will have a component which is minus dEz. Hence the Z component, AZ component will cancel in the integration process, and we need only to integrate our term which is dEr. So our total electric field intensity, which are only lies in the radial component, so we will have to integrate them from minus infinity to plus infinity. As in the radial term ER we have a dz term, so our integration will be with respect to z-axis, and the z-axis for the infinite line is for the limits of the z-axis for the infinite line is from minus infinity to plus infinity. By solving this integration and multiply this result with the outer term, our electric field intensity in the radial direction due to infinite electric line of charge is equal to rho L divided by 2 pi epsilon naught into R, and the unit of electric field intensity is volt per meter. So let's sum up our lecture. What we have discussed in this lecture, we discussed an electric dipole which is a combination of two charges having same magnitude but different behavior, and they are separated by a small distance, and we have obtained an expression for the electric field intensity due to an electric dipole at a distance I. And we have also discussed the electric field intensity of a continuous charge distribution, in which charge is distributed over a three-dimensional space or over a plane or a single dimensional line. And we have discussed their electric field intensity, and will also discuss the example related with the linear charge density, in which the charge is distributed over an infinite line, and we obtain an expression for the electric field intensity due to infinite line of charges. In next lecture we will discuss about the flux density and the Gauss's law, which is the fundamental law of electrostatics, and this is also known as the first equation of Maxwell equation. So we will discuss its differential form and the integral form as well. So if you have any difficulties related to this lecture, you can contact me at my email. Till then, Allah Hafiz.